Hi everyone, I'm Rishi Panchal. Welcome back to the channel. Here's something shocking. For decades, semiconductor manufacturers expected that up to 90% of their chips would fail. That's right. In the early days of memory chip production, yields as low as 2% were considered normal. But today, companies like TSMC are achieving around 80% yields on 4-nanometer processes, technology thousands of times more complex than those early chips. How did we go from accepting massive failure to achieving such precision in one of the most complex manufacturing processes humans have ever created? The answer involves a hidden revolution in how we spot defects, a revolution that transformed semiconductor manufacturing forever. In this video, we're going to explore how automated inspection tools revolutionized chip fabrication and helped create the technological world we live in today. To understand how revolutionary automated inspection was, we need to understand what came before it. In the 1960s and early 70s, wafer inspection was surprisingly primitive. Human operators would literally sit at microscopes for hours, manually scanning silicon wafers, trying to spot defects that were often smaller than a micrometer. That's 1,000th of a millimeter. Think about the challenge. A single 4-inch wafer could have billions of potential defect locations. And these inspectors weren't just looking for obvious problems. They were searching for microscopic imperfections that could cause an entire chip to fail. Research on these human inspectors revealed some concerning trends. Effectiveness varied between operators by a factor of 5, even with identical training. Performance within a single shift would start low, peak about a third of the way through, and then decline as fatigue set in. Even at peak performance, human inspection accuracy never exceeded 87%. Defect classification was highly subjective, making it impossible to reliably compare data over time. Its subjectivity was particularly problematic. Since every inspector might classify defects differently, manufacturers couldn't tell if their processes were actually improving or not. They lacked standardized metrics. And the results were clear in the industry's struggle with yields. Let me share some rare data from the 1980s, compiled during the US-Japan semiconductor trade dispute. When both American and Japanese manufacturers began producing 16K DRAM chips in 1978, yields started at an abysmal 2%. 6 years later, by 1984, American yields had only improved to 36%, while Japanese manufacturers reached about 48%. That 12% gap in yields accounted for roughly 80% of the cost difference between Japanese and American chips. The industry desperately needed a more reliable way to find and classify defects. The human eye and human judgment simply weren't good enough for the rapidly advancing technology. The first step toward automation came not with wafer inspection itself, but with the inspection of photomasks. Photomasks are essentially the templates used to print chip designs onto silicon wafers. Think of them as the master copy. Any defect in a mask would be replicated across potentially thousands of chips. While individual wafer defects might be tolerable, mask defects were catastrophic. The problem? Manually inspecting a single 4-inch mask could take between 4 and 20 hours. With 6.4 billion possible defect locations on such a mask, human inspectors frequently missed critical flaws. Studies found that about 20% of masks that passed human inspection actually contained defects. The first major breakthrough came from Bell Labs in the early 1970s with a system called AMIS, Automated Mask Inspection System. AMIS compared two dye images side by side using 2-3 micrometer wide laser beams. When the system detected differences between the images, it flagged them as potential defects. AMIS wasn't perfect. It struggled with mechanical alignment issues and temperature fluctuations that could cause false positives. It couldn't detect repeated defects or determine if a defect would actually kill the chip. And it couldn't spot anything smaller than 2 micrometers. But AMIS offered something revolutionary: consistency. For the first time, manufacturers could compare inspection data across months or years, giving them insight into whether their processes were actually improving. While Bell Labs' AMOS was groundbreaking, it wasn't commercially available. The industry needed someone to bring this technology to market. Computer Vision had acquired a small invention that automatically aligned wafers with photomasks for exposure, a task previously done manually with microscopes. Levy led the effort to commercialize this technology, but eventually caught the startup bug. In 1975, he and his CFO left to start KLA with $600,000 in venture capital. In 1978, KLA launched their first product, the KLA 100. This automated photomask inspection system transformed the industry, reducing inspection times from 8 hours to just 5 minutes for a 3-inch mask. Later systems like the KLA 200 series added the ability to compare mask images to reference designs stored in databases. These early automated mask inspection tools revealed something shocking to fab operators. Their actual wafer defect densities were far worse than they had thought. But this revelation also pointed to a solution. If they could systematically find and categorize wafer defects, they could either rework problematic wafers or eliminate the causes of defects entirely. The real game changer came in 1984 when KLA released the KLA 2020, the first automated inline patterned wafer inspection tool. This system integrated directly into the production line, allowing for continuous monitoring rather than isolated testing. At its core, the KLA 2020 was an automated, illuminated, high-speed camera with an attached microscope. It would take pictures of the wafer at various magnifications, defined by pixel sizes, ranging from 10 microns down to 2 microns. The system's computer would then compare these images to neighboring die to identify defects. The KLA 2020 used what's called bright field illumination, where a light source directly illuminates the die to make features more visible. This approach produced clear, detailed images that could be analyzed for defects. Semiconductor manufacturing involves hundreds of complex steps, but manufacturers couldn't afford to inspect wafers after every single one. Instead, they identified critical control points where inspection would provide the most value. Lithography became one of these key inspection points. In this process, an exposure tool projects ultraviolet light through a mask onto a resist-coated wafer. After exposure, the wafer goes through development to harden the resist before etching. Since the etching process is permanent, literally cutting into the silicon substrate, it made sense to inspect wafers after development but before etching. This allowed manufacturers to catch defects like bridges or gaps in design patterns, or alignment issues before they became irreversible. A rare case study from Yamagata NEC Corporation demonstrated the power of automated inspection. When they implemented the KLA 2020 for inspection after an aluminum etching step, they found the machine was 5 times faster and caught 10 times more defects than human inspectors. These automated inline inspections transformed how fabs monitored production. When an inspection tool found something wrong, operators could be alerted immediately, allowing them to pull affected wafers from the normal flow for rework. Even more valuable was the ability to trace defects to their source. At leading fabs like TSMC, there's actually video recording of every wafer's journey through the production line. During defect review, engineers can analyze this footage to pinpoint exactly when and how a defect occurred, helping them eliminate the root cause entirely. Early inspection tools weren't perfect, though. One major issue was discerning between critical and non-critical defects. Without proper filtering, tools would flood operators with false alarms about harmless variations. And the biggest complaint: speed. The KLA 2020 could only inspect about 0.1 100mm wafers per hour. This meant manufacturers typically had to sample wafers rather than inspect every single one, a bit like occasional air quality testing rather than continuous monitoring. KLA wasn't alone in recognizing the opportunity in automated inspection. Other companies entered the market with different approaches to the same problem. Around the same time as the KLA 2020's release, Tencor introduced the Tencor 7000. This system used a completely different approach called dark field illumination. Instead of directly lighting the wafer, Dark field involved firing a laser at the surface and examining how the light scattered. Particles on the surface would cause distinctive scattering patterns that could be detected. Dark field didn't provide the same level of detail as bright field illumination, but it was cheaper and offered much higher throughput. This made it particularly useful for particle detection and surface inspection. The complementary strengths of these two approaches ultimately led to one of the industry's most significant mergers. In 1997, KLA and Tencor combined in a massive $1.2 billion deal, creating KLA-Tencor, now simply KLA Corporation. Today, KLA is one of the semiconductor industry's giants, with a market capitalization around $100 billion. This merger marked a recognition that comprehensive inspection required multiple technologies working in concert. No single approach could catch every type of defect at every stage of the increasingly complex manufacturing process. As semiconductor manufacturing advanced to smaller and more complex geometries, inspection tools had to evolve rapidly to keep pace. The biggest early challenge was throughput. Early inspection tools were simply too slow for comprehensive coverage of production wafers. Toolmakers addressed this in several ways. In the 1990s, they integrated faster computers for more efficient image processing. They also added the ability to compare wafer images directly with stored data files of chip designs, rather than relying solely on die-to-die comparisons. The 2000s brought a major transition from charge-coupled devices, CCDs, to CMOS image sensors for capturing images. This significantly increased image acquisition speed and opened the door to more sophisticated digital processing techniques. Like KLA later adopted what's called broadband plasma or BBP technology, where a laser ignites a plasma to generate intense light across a broad range of wavelengths, from visible to ultraviolet. Interestingly, KLA emphasized that their key metric wasn't resolution. They weren't trying to create the finest possible images like lithography machines. Instead, they focused on contrast or signal-to-noise ratio. They wanted defects to stand out clearly, and tuning illumination to different wavelengths could help make specific types of defects more visible. In recent years, inspection tools have begun using deep UV wavelengths to capture even smaller defects, potentially as small as 10 nanometers. As feature sizes continue to shrink, we might eventually see EUV-based inspection tools, similar to the advanced lithography systems used in cutting-edge manufacturing. Today's inspection tool market has evolved into distinct segments serving different parts of the semiconductor manufacturing process. KLA remains the dominant player in the high-end market, particularly for front-end inspection, the wafer fabrication steps that require the most precise measurements and the strictest cleanliness standards. These high-end tools command premium prices due to their critical role in yield management for the most advanced process nodes. Other significant players in the high-end space include Applied Materials and Hitachi High-Tech, though with considerably smaller market shares than KLA. The lower end of the market focuses on back-end processes, assembly, testing, and packaging that occur after the wafer fabrication is complete. These applications have somewhat less stringent requirements, and consequently lower-priced tools. Companies like Rudolph Technologies, which entered the inspection business from microscopes, developed specialized tools for examining packaging features like bumps, redistribution layers, and through-silicon vias, TSVs. In 2019, Rudolph merged with Nanometrics to create Onto Innovation, now a significant player in this space, alongside companies like Camtek. The entire inspection tool industry is estimated to be worth between $5 to $8 billion annually, a relatively small but absolutely critical segment of the semiconductor equipment market. Without these tools, the extraordinary yields of modern semiconductor manufacturing simply wouldn't be possible. As chips continue to shrink and grow more complex, the definition of what constitutes a defect becomes increasingly strict. This makes the job of inspection tools even more challenging and more vital. One of the most exciting developments on the horizon is the expanding use of artificial intelligence for identifying and classifying defects. With sophisticated AI, future inspection systems might not even need reference images to flag and categorize defects. They could recognize problematic patterns directly. However, semiconductor manufacturers are notoriously conservative, and for good reason. Their process nodes operate for years, and changes, even seemingly beneficial ones, are approached with extreme caution. The art of yield management is a long, slow slog. Behind every improvement in yield curves are the accumulated efforts of thousands of workers, inspecting, troubleshooting, and fixing defects. It's a technical miracle made possible by the combination of sophisticated microscopes, advanced computing, and good old-fashioned human perseverance. The story of semiconductor inspection tools reminds us that sometimes the most important technological revolutions happen behind the scenes. The devices we rely on every day, our phones, computers, cars, and countless other products, owe their existence not just to brilliant chip designs, but to the unsung heroes that make sure those designs actually work when manufactured. If you found this deep dive interesting, please like this video and follow me for more such content.